very much. Good afternoon. I would like to thank the organizers for being so gentle as to allow for a little bit of more of mathematics and sort of possibly more fundamental mathematics, and also being I need to apologize. This seems to not essentially proper. To talk about fundamental things of general relativity at a relativity conference. But I'd like to advertise a sort of new look, a different look at the three fundamental objects, so three fundamental tensors of general relativity, which is the metric tensor, the Einstein tensor, and the third one, which is the torsion, which is usually not present in general relativity as such. I mean, it's present in the version of Einstein compound. All right. So the thing is, something like physics versus mathematics. So, of course, from the physical point of view, look, we know what is metric. We basically know what is metric. You can have different approaches to that. I mean, different looks at it as distances or tensors. We know what is the curvature derived from the metric, and so on and so forth. But I mean, in a mathematical point of view, I mean, there is a different possibility to look at those things. And different means first sort of global. I mean, what we usually do, I mean, looking at the metric tensors, looking at the points, so looking in a very, very localized way. Now, is there a way, I mean, there's a slightly different point of view, which is more global, and uses some certain mathematical tools that have been developed in the last, say, 40, maybe 50 years. The second thing is that this different look is much more, so to say, easier to use for any possible generalization of general relativity, and especially when people talk about approach to quantum gravity and looking at the space-time and Planck scale, or possible modifications of gravity, possible ways to quantize gravity starting from the looped quantum gravity, random triangulations, or deformations of quantum space-time, which are so numerous approaches to that and numerous guesses. Then having a different look at those objects, which are fundamental to understand gravity, is something interesting. I mean, possibly not the final answer, but something that could help us understand it better. So the question is, I mean, what are those fundamental things from the point of view of mathematics understood and understood in a global way? And this global way is going from tensors, I mean from the objects which are local, to something which is more global. I mean, albeit could be expressed in a local coordinates localized way, so going to operators. So the idea is to switch notion of geometric objects from tensors, scalar functions tensors, to differential operators, and work, I would say, not only exclusively, but work mostly with differential operators. I mean, all over a manifold, so it simply means you have a manifold in background, you have some vector bundle, sections of a vector bundle, and you act with a differential operator on it. Now, what are the tools of that? And the tools is quite nice, and it's been, around us for some time, and it's spectral geometry. And spectral geometry, arises from this question, posed years ago by Mark Katz, and can one hear the shape of the drum? And of course, we know the answer is no, but certainly, a lot of the information is contained in the spectrum of differential operators. And especially, this is what we learn basically during our studies when we compute the spectra of Laplace operator, compute the spectra of even of the Schrödinger operator, which is just generalization of differential operators with some added extra terms which are potentials. Now, the tools of spectral geometry, well, I will say about two tools that could be used. So think both related, I will not go into that. But there's a very nice tool that's been also around for some time, which is just the asymptotic expansion of the heat trace. So basically you have an operator, differential operator, of course certain differential operator, like a Laplace operator, so first order or second order elliptic operator over a manifold. We're talking about Riemannian manifolds, so the Euclidean signature for now. And then if you just do the usual thing, the exponentiation e to the minus t, this operator, this is a trace class operator, and you can just compute the trace, the usual regular trace over the, of course, infinite dimensional Hilbert space, but still is a number. But if you consider it as a function of t, then there is something which is called asymptotic expansion, and this asymptotic expansion, so this here, I mean, starts with the negative power of t, and it gives some coefficients, and it is quite surprising. I mean, it's been quite a discovery that these coefficients carry a lot of geometric information. And this geometric information, I will go to that, I will jump a little bit, maybe. This geometric information in the first of this coefficient is, for instance, the volume of the manifold. So, the volume of the manifold, you can just simply, I wouldn't say guess, but you can compute from the spectral of the differential operator, just looking at itself, sort of asymptotics over there. But in this coefficient, so in this sort of functions of this operator, you can get a little bit more than the volume. You can get also the integrated scalar curvature, and then integrated some scalars over the manifold, which will be something like the square of the Riemann tensor, and so on and so forth. So the more you go, I mean, the more complicated, geometrical objects you can obtain. So this is the first tool. Yes?
This is valid for compact manifolds.
Oh yeah, this is for compact closed Riemannian manifolds. You can, of course, but you can make it for locally compact. You can put a test function in front of it. So just this is a functional here. Just of the operator, if you put a function here, which will be sort of compact support, you can make it for locally compact manifolds as well. Now, the second tool, which is sort of more easily used, more practically used, and this is quite nice, is the existence of a unique trace over an algebra of differential operators. So this is slightly, more generalized. So you don't take an algebra of differential operators, so operators of finite order. But you also allow the inverses, so to say, quotation mark, inverses of these differential operators. And you have this full algebra, which is the algebra of pseudo-differential operators over a manifold. Then, this algebra has a fantastic thing, which is, sort of mathematical nice object, which is the unique trace. Absolutely unique trace over this algebra, which is called Wojcicki residue. It has been discovered by Jagiellonian and Wojcicki in the 70s, 80s of last century, and it has a very nice local expression. So, for the pseudo-differential operators, I mean, you take a symbol of order minus n, the dimension of the manifold is n, so you have an n-dimensional manifold, you do some integrals, and you get a Wojcicki residue, you get a trace. And, using this trace, so either using the hit trace, hit kernel, or using this Wojcicki residue, you can get some geometric objects. So these geometric objects are like, first, so this is here written using this Wojcicki residue, rewritten using this hit trace coefficients. So first, the Wojcicki residue, if you take the Laplace operator to the power minus n, and you compute the Wojcicki residue of that, and this is for the even dimensional manifolds. Could be done for dimensional manifolds, but I mean, for simplicity, we consider even dimensional ones. So we take to the half dimension, negative power half dimension Laplace operator, and you compute the Wojcicki residue, you get volume. Well, some universal constant in volume, and you can localize it. So localize it means, you can take a function, arbitrary function, and compute, this function for this function, and you get the integral of this function. This is, so far so good, nothing, very important, just the volume. Of course, you can interpret it, from the, so to say, general relativity point of view or cosmology point of view, like the part of the action, like, cosmological constant. Now, what is more interesting is that you can go further. So you can go and compute, for instance, the integrated scalar curvature. And this is the next step, and there's been, actually, you know, in the Higgs phase, it's been known since the 80s, 90s. Then it's been around in the early years of this century, it's been done in completely different ways. I'm using this Bourdieu's residue. So if you take and compute this unique trace on the negative power of -n plus 1, what you get? You get just the Einstein, well, you can call it Einstein-Hubert action, the integrated scalar curvature. And you can localize it as well. So you take a function, this function could be just, you know, centered around the point, and you can localize it, so basically you can recover scalar curvature at this point. So these are these two functionals. Well, what is the, so to say, benefit of it? I mean, you don't start with whatever is metric tensor, you don't need to do what is Riemann curvature, compute everything. You just have absolutely, you know, fundamental formula which just uses nothing but some fundamental properties of the Laplace operator in this case. So second order differential operator, elliptic operator, which is just the Laplace operator. Now, these are scalar functionals. Scalar functionals are very nice, for instance, for the action, but can we do more? So can we look a little bit, you know, deeper and get some object-like tensors? And this is, you know, was the result of joint work with Jagiellonian and yes?
Sorry, I forgot, what is the relation between m and lowercase m and lowercase n?
M is n half. So
yeah.
the manifold is dimension 12. Yeah.
I remember. And n?
N is the that dimension of the manifold.
Ah.
So we take the manifold, given dimensional manifold, and
Okay.
is 12. It could be now 4-dimensional, but just for simplicity.
Now it is.
Yeah. So this is joint work with L.Dabrowski from spacetime and PhD student P.Zalecki. And, well, what we did, we basically generalized it for tensors. So this is something, you know, how to write the metric tensor, how to write, surprisingly, not the Ricci tensor appears as sort of more fundamental, but as more fundamental object in this case appears the combination of Ricci tensor and metric tensor, which is the Einstein tensor. So the idea is quite nice. Yes?
So the Laplace operator here is a scalar operator? Or
Yeah, in this case it's a scalar operator. But I mean, it could be generalized to the lift of Laplace operators, for instance, to the spinor Laplacian or Laplacian over acting on some sections of a Drexel band. So no problem with that. This is, I will mention it later. But just, you know, taking the usual scalar Laplacian and two vector fields. Vector fields, I mean, are just differential operators. I mean, this is how we understand also vector fields. Then we can just, you know, compute the Bourdieu's residue of such an expression. This is a differential operator, which is a combination of V, W, and the Laplace to a certain power, negative power. And what do we get? Actually, something proportional to the metric. So this is the metric function, or what we call the metric function. I mean, for these compact closed Riemannian manifolds, it just recovers the metric. What is more interesting is if we go one step further, so not here -n-1, but just -n. So this is operator of order 1, this is operator of order 1, this is operator of order -2m, so to say. So the entire thing is, you know, of order -2n plus 2. And if you compute it, it gets, again, you get again a functional. I mean, here I don't use any function because vector fields, and you can incorporate any function into vectors. You can localize vector fields. So what you get the exactly on the spot Einstein tensor. So this is how you can express the Einstein tensor and the metric tensor and the Einstein tensor using something which is, you know, global, spectral. So basically this depends on the spectrum of the Laplace operator and on these differential operators. Yes?
Sequence of those operators is not important, yes? I can put first in
Oh yeah.
and then Laplacian doesn't matter.
Absolutely, it doesn't matter. It doesn't matter. It's not obvious, you know, so say from the look of it.
Because of this is straight.
Yeah, because this is space, yeah. Yeah. Yeah.
What is exactly this operator inside the script W?
Yeah.
So we first act on a scalar function with delta to -1, and then
with a vector
a
field.
vector field
And then with another vector field, yeah. So vector fields act like derivations on the algebra of self. C infinity functions, and so this is, and the order of course doesn't matter. So this is quite, I mean, this comes as a result. I mean, that it's really symmetric in this case. Now, so far so good, but you know, this been, you know, for a scalar function and scalar Laplace operator. Nice thing is that it could be generalized to, so we can limit everything to the vector bundles. So we can act with operators that act on sections of vector bundles. And, well, there's one very nice particular vector bundle that we like, and it appears in physics, which is the spinor bundle. So we can act on spinor, so we can lift, for instance, the Laplacian to be the spinor Laplacian, and, you know, just compute it. Once again, I mean, I will not give you the details, but there's one thing which is also interesting. I mean, if you have a spinor Laplacian, then you basically can take a square root of that. So you can work instead of second order differential operator with a first order differential operator, which is this nice square root, which is just the Dirac operator. So how does it look like? How does it work when you work with a Dirac operator? And this is also quite nice. I mean, you can do just the same, but you need to slightly reverse the thing. So you need to go to the dual picture, because with the Dirac operator, you have the spinors, and the thing that you can nicely, of course, you can represent the vector fields acting on as cells and derivations on spinors. But there is a nice thing that you can also represent on spinors, and you can represent the differential forms via Clifford multiplication. So this, you know, opens a new possibility, you know, to look for the dual tensors. So non-dimetric tensor defined as a function over vector fields, but the dual tensor, which is a function over the differential forms. So here, you know what we have? We have two differential forms. And what do? I mean, this V and W are differential forms. V hat and W hat are just a Clifford multiplication by differential forms on spinors. D is the Dirac operator, the genuine Dirac operator. When you have the spin manifold, you can have the Dirac operator. And then you define the metric functional just like that. So you take the multiplication by one form, second one form, and d to the power minus n. I should have put, I mean, here is the even dimension. I still working with even dimension, so it doesn't matter whether I put that epsilon value or not. And the interesting thing is, I mean, that the formula for the Einstein tensor is changed slightly. I mean, it's just a little bit more complicated. It's just V and then the anti-commutator of D with the second form, and d to the minus n plus 1. The thing is, I mean, it doesn't look very symmetric, but it is. I mean, this is again, you know, there's a property of the trace and property of the Clifford multiplication that it makes this, you know, quite symmetric. And those two functions, which are again defined abstractly. So basically, when you have Clifford multiplication, when you have the Dirac operator, you just compute them. And this means that even if you don't work, you know, localized, if you work only with spectrum, if you work with abstract operators as operator algebras, then you can compute it. You can compute what is the metric, you can compute what is the Einstein tensor. All right. Is there anything more? Yes. I mean, for instance, I mean, there's been, you know, a question around what is really torsion. Of course, you know, when you start with the usual approach to differential geometry, linear connections, you have the linear connection and you say, what does it mean that the linear connection is torsion free? But here, we start completely differently. We work with operators. So what does it really mean that the Dirac operator, say Laplace operator? Here we formulated it for the Dirac operator. What does it mean that there's torsion free? So there's no torsion in the theory. A priori, there could be torsion, you know, you can have Einstein-Cartan theory. But there's a very nice function. You can express, I wouldn't say everything, but you can express a lot as functionals. And this is the function, you know, over 3 differential forms. Because, I mean, torsion, I mean, is something like the tensor, I mean, 2, 1, 2, or you can take contortion, I mean, 3, 0. It is just a function, you take the product of the 3 differential forms, d, and then d to the power minus n. And it really computes the torsion tensor, the part of the torsion tensor that is in the Dirac operator, because not all of the torsion could be in the Dirac operator, only some parts. Now, what are the applications? Of course, you know, from the point of view of differential geometry, you can say, I mean, this is nothing, because we usually work with local metric tensor, and then we can compute what's the Riemann curvature, and so on and so forth. So, you know, for standard things, you know, that you know you usually work with, this might not be, you know, anything, you know, very deep, and anything, you know, helpful. But it's, you know, sort of a generalized point of view that could be applied for a lot of, you know, extensions of geometry. In particular, you know, the thing that we did, I mean, we computed for the spin manifolds, but we also computed it for the so-called Dirac-Hodge operator. So, I mean, sort of natural operator that comes with any Riemannian manifolds is, I mean, if you take the complex of differential forms, you take the d exterior derivative, you add to it is a joint, so basically the Hodge star of it. Then you have a natural first order differential operator, which is called Hodge-Dirac operator, and you can compute the Einstein tensor, the metric tensor, and show that this is really torsion free. This is, you know, so far, you know, the only way. So it's come to the extensions of what we understand as differential geometry, what we understand as, you know, the approach, you know, to possibly, you know, quantum spacetime. So the extensions are, you know, that was, you know, computed in mind, and that was, you know, done in mind with these extensions, you know, that allow for certain perturbations of quantum space-time to quantum space-time. The models that are based on Popeye racemmetries or certain deformation, Maillard-type deformations in the background. So then, you know, this has always been a good point, you know, how to define, how to extend, what is a metric? What is a metric? What is the Riemann curvature? How to access, you know, this part of information. Now, working with the differential operators, instead, you know, of point-like, you know, objects, has a huge benefit. And this benefit is that, yeah, you look from the global point of view, but then you make sense, it makes sense. It makes sense, you know, to define what is metric for, you know, to use a tori. For instance, which is the classical example, is like the compactified sort of version, or for the Maillard deformation. For the quantum deformation, including possibly, you know, this Q deformation, so we, for instance, computed that certain Dirac operator for the quantum SU2, which is quite well known and been sort of invented in war, so is torsion free. For something which has been around for a certain couple of years in relation to the standard model, which are the modifications of geometry by adding something which is finite. Finite means like discrete, but discrete also in terms of discrete algebras, finite algebra, matrix algebras. So everything, you know, all these objects could make sense. I mean, are not meaningless, are meaningful in this generalizations that could be computed. So this is, you know, what's been done. What's the output? What's possible? What are the possible things? So, of course, you know, there are various approaches, you know, to certain modifications of geometry with torsion, legislative connection, and so on and so forth. We propose the spectral point of view, which is one vast, and then there's a way, you know, to compare it with the others. Study these quantum metric spaces, especially those that are relevant, you know, for certain deformation that's been around, you know, those for double special relativity, the couple deformation, and so on and so forth. Now, even within the, you know, classical world, there is a way, you know, of this to have a global look at something which are orbital, so things with certain singularities around. So this global approach might be finite, and also, you know, for the flat manifolds, because then we, for instance, I mean, there's been a good question, and there's been around, you know, examples of like certain geometries, certain non-commutative, deformed geometries around, I mean, like tori, like spheres, and there's been around the question, okay, what is the relation? For instance, can we say meaningfully what is an Einstein manifold, Einstein non-commutative manifold, or generalization of Einstein manifold, or flat manifold? And this allows it. I mean, we can make certain conjectures, we can make certain propositions what these objects are. But of course, you know, the price for that is that you need to have this global spectral approach. So I think I will thank you very much for your attention. These are the references. So this is mathematics, this first paper with Ludwig and Pavel in advanced mathematics, and we have 2 more recent papers on that. Thank you very much.
Thank you very much for the talk. Are there any questions or comments?
I must confess that I'm very much impressed by these formulae. Being a modest physicist, I did not know them, but they are very nice, but it is, in a sense, a perverse view of geometry, because in geometry, normally we begin with local objects, then we globalize them by integration or something like that, which means that we express global by local. In a sense, you go in an opposite direction. You want to explain local by global. I think it's very, very interesting.
Yes, indeed. I mean, this is the, I mean, perverse maybe is not a very good word, but I mean, it is a way of expressing things that are first global. You can localize them in a certain way by using these functions which are localized around points. But yes.
Does this formalism also apply, or can it be generalized to the case when the connection is non-metric, because the connection and the metric are 2 dependent objects?
Well, the formalism, I mean, I wrote here, you know, something like a formula for using this Wojcicki residue. This Wojcicki residue exists. Just as it. If you have an algebra of this, so the differential operator, it just exists. It doesn't depend on anything. It doesn't depend on metric. Now, the question is, if you start with a differential operator, the good question is, what gives you a differential operator? And the answer is, a differential operator gives you the metric. And you can express it, I mean, here's the formula for the metric, so say metric tensor as a functional. But you can also say it in terms of distances. There's a formula for the distances. So basically, I mean, you can say, you know, linear connection or something like that. This is secondary in this approach. The first object in this approach is a differential operator. And the rest, like the metric, curvature, is inbuilt. You get out of it. It's not that you define a metric. Having a differential operator is like having a metric. That's it. So this is not like, you know, and then the rest, I mean, I don't bother about linear connections. I mean, this is sort of algebraic construct. Here is a sort of like spectral construct.
Thank you.
More questions? If not, let us take a